All right, we're talking about V caps, all right, voltages and just how capacitors work. So what I did is I just drew 3 capacitors series to a 12-volt battery. All right, now what you need to understand is this battery is going to send Q right to there. But that's where the Q gets stuck because it's just like a fish that bumps its head. Damn. It can't move, right? So there's only so much Q that can go here, and I just made up a number. Let's say it's +4, because that's the positive terminal of the battery. So if this piece of metal now is +4, then since Paula Abdul taught us opposites attract, this positive is going to pull 4 negatives over to this side of that capacitor. So if this happens to be +4, that's going to be -4, right? And if those electrons left this piece of metal to go there, then what remains here is a charge of, very good, +4. And then that pulls -4 to here, which leaves this +4, which leaves this -4, which means regardless of the size of the capacitor, a 3 microfarad, a 2 microfarad, a 1, doesn't matter the size of the capacitor, in series they all have the same Q because that Q came from the battery and it bumped its head right there, and that's all the Q can do. So this whole thing has an overall consistent same amount of Q. The Q then at capacitor 1 is the same as the Q on capacitor 2, is the same as the Q on capacitor 3, same as Q on capacitor 4. So then knowing that Q is CV, and what you also remember from resistor circuits is voltage adds up in a series circuit. Since the voltage adds up, another way to say V is Q over C. So the total Q divided by the total capacitance is the VT. It'll be the same as the voltage across capacitor 1 plus the voltage across capacitor 2 plus the voltage across capacitor 3. All right? Since all of these Q's are clearly the same, then I can kill the Q's, and they add up inversely. All right, so the 1 over the total capacitance is 1 over the C1, 1 over C2. So now I add up what I named or called the capacitors, 3 micros, 2 micros, plus 1 micro, but you add them inversely. So this is a case where 3 plus 2 plus 1 clearly equals about a half. All right, so it's 0.54 microfarads. That's the total capacitance. If that's the total capacitance, then we can use that total capacitance to get the total amount of charge on those capacitors. The QT is CTVT. The QT then is that total capacitance, 0.545, times the voltage from the battery is 12. So the amount of Q on any of those capacitors, all 3 of them have the same amount of Q, is 6.5-ish microcoulombs. That's the amount of Q on any one of those 3 capacitors, all right? Even though they're different size capacitors. But what then you need to realize is over here that since Q is CV, they all have the same Q. So if you have a large C, you're going to have a little V. Adorable. If you have a small capacitor, you're going to have a large V, and so the way we calculate the voltage drop across these, because you know if I put a voltmeter across all 3 of them, the total voltage is going to be the same as the battery. But if I put a voltmeter across any one of those 3 capacitors, the voltage will add up to 12, and so to calculate volts is just Q over C. And the Q of any one capacitor is the same as the total capacitance. So it's at 6.5 micros divided by the 3 that is this capacitor. So the voltage drop across this capacitor is a little over 2. The voltage drop across the 2 microfarad capacitor is that same capacitance, or the same charge divided by its capacitance, so it's a little over 3. And then this guy, the littlest capacitor, 1 microfarad has the largest voltage drop, 6.5. So 6.5-ish plus 3.25-ish plus 2 and a little bit-ish adds up to 12. All right, but again, the key to remember in series is, again, it's like some of you on prom night, it's got no options. So it bangs into this here, and that charge then is distributed through all of those capacitors, which is the big difference between these and parallel capacitors. So I just threw the exact same 3 capacitors, a 3 micro, a 2 micro, and a 1 micro, but I put them parallel to each other. And the key difference here is when that positive Q leaves that battery, right here it's got options. Some of those fishies will bang their head here, some of those fishies will bang their head here, and some of those fishies will bang their head here. So any one way that they choose, they'll still bump their head. They can't go past that one, but a larger capacitor can hold a greater amount of Q. So I just said, okay, maybe 3 fishies bang their head on this one, maybe 2 bang their head on this one, and maybe 1 bang their head on this one. But the total amount of Q then in this parallel branch will add up in parallel. Q adds up in parallel, the same way as current adds up in parallel. And again, it's a conservation Q. Where did all those positives come from? They came from the battery. So this battery lost a greater amount of Q in parallel than it did in series. All right? And Q is CV. So all I have to do is multiply the capacitor times the voltage to get 12 microcoulombs of charge on this one, 24 microcoulombs of charge on that one, because it's just 2 times 12. This one's just 3 times 12, 36 microcoulombs. The total amount of charge then, 12, 24, and 36 is 72. All right? You guys all know that the voltage across these stays the same, but the Q adds up, QT, CT. So now here we can tragically kill all the V's. It's the CV, the CV, the CV, the CV. So the total capacitance then is just a normal adding of the capacitances individually. So if it's a 3 and a 2 and a 1, this is a case where 3 plus 2 plus 1 clearly equals 6. So the total capacitance is 6. The total charge is 72. And so QT is CTVT. We can double check that. The total amount of Q, 72, is the total capacitance, 6, times the total voltage, which is 12. So parallel, I think, is a little more conceptually logical. It makes a little more sense. The series one can be a tad more confusing, but again, what you got to remember is the Q can only come from the battery. So if the Q gets stuck in a series circuit, that Q is evenly distributed throughout each capacitor, so every capacitor has the same charge on it. In a parallel branch, the Q has options, so depending on the size of the capacitor is how much Q can build up on it. So you can use this strategery, in some of the circuits when, if you have complex circuits like this, where if you got a couple of capacitors in series, add them seriously, and then these happen to be parallel to this one, so you can add these two together parallelly to get the total capacitance of that particular circuit, and just apply those to different circuits and different whatevers, and yay physics.